Hello everyone, a very good evening to you all. Welcome to SPSVERSITY. So today I'm going to take the topic electrochemistry from grade 12, and here we are. I'm just waiting for 2 more minutes to start the session, so all the school going kids, they can come back and they can join the session. So exams are nearing. I think all of you are preparing well for the exams. Yeah, here we go. So we know that the electrochemistry consists of two parts. Whenever you say electrochemistry, it has two parts in the name itself. One is the electro, the other one is the chemistry. So the electro is related to electrons, and the chemistry is related to the chemical energy. So here there are two energies which are interconvertible. One is the energy which is obtained from the electrons. That's how the electrons are produced. This is by the redox reactions. You remember what exactly a redox reaction from the previous years. So electrochemistry is a branch of chemistry which deals with the study of production of electricity. So the electric energy and the chemical energy can be interconvertible. That's what we study in this topic, and how they are interconvertible and where do we use this. So the importance of this topic is production of metals. So if you say the electrochemical series, or the metals which are very reactive, that's a group 1 and the group 2 elements. These group 1 elements are not found in the native state because of their high reactivity. And if you have to produce those metals, then you must have some knowledge of electrochemistry, because you're going to produce them through the electrolytic cells and the electroplating and anodizing. All this are related to electrochemistry. And how do you purify the metals, and which reducing, which oxidizing agent you are going to use for metals, and the batteries and the cells which are used in the instruments like your watches, then the car batteries, the inverter batteries. All this have the applications of electrochemistry. So here in this particular topic, we are going to see that the electric energy and the chemical energy are interconvertible. So how the electrical energy is produced? Electrical energy is produced by the movement of electrons. We know that electricity is due to the movement of the electrons. And how do you get this electrons? And how is it converted to chemical energy? So if there is a redox reaction happening, what exactly is a redox reaction? It is a combination of both reduction and the oxidation, and which take place simultaneously in a reaction. Reduction is nothing but the gain of electron, and the oxidation is nothing but the loss of electron. Okay, so because of this, the electrons are generated and they carry the current. This is how the chemical energy is connected to the electrical energy. And in this topic, we come across different third terms. One is the electrode. Electrode is a metal rod which is kept in the electrolytic cell. And then you have the electrolyte, that is made up of ions, either in the molten state or in the aqueous state. And electrolysis, it is a process where you decompose the electrolyte. Say, for example, if you take any electrolyte like copper sulfate, by passing your current, you're going to decompose it into Cu2 plus and the SO2 minus ions. So here the electrolyte is going to decompose by passing the current. Okay, so and the electrochemical cell, it is going to consist, the electrochemical cell is going to consist of the electrode, the metal rods, electrolyte, that's the one which is going to decompose by the passage of the current. And in the electrochemical cell, it is a device which converts the chemical energy into the electrical energy. Here the chemical energy is generated due to the spontaneous reaction. That's a redox reaction. The reaction is spontaneous. What do you mean by spontaneous? The reaction which can happen by itself. Once it is started, it just happens by itself. Like you are very much interested in studying and you study on your own. If it is non-spontaneous, someone has to push you to study. That's called as non-spontaneous. In this reaction, once it is started, the reaction proceeds by itself, and that energy generated is the chemical energy that gets converted into the electrical energy. Okay. So whenever you say the electrochemical energy or electrochemical cell, there are two basic type of cells that you have to remember. One is the galvanic cell, the other one is the electrolytic cell. What exactly is the galvanic cell and what exactly is the electrolytic cell is what you have to see. So galvanic cell is a device where you produce the chemical energy. So there is a redox reaction that produces the chemical energy, and so due to the chemical reaction, the electrons are generated. So this chemical energy is converted to the electrical energy. So there are reactions, and in the reactions, electrons are produced. That those electrons generate the electricity. And then electrolytic cell, it is a device where the reverse is happening. What exactly it is? You pass the electric current and there is a chemical change. Okay, so either the chlorine which is present in the sodium chloride that gets that's a NaCl, the Cl maker get converted to Cl2, like this. And in case of galvanic cell, whenever you say galvanic cell, the sign conventions you have to remember: the anode is considered as negative electrode and the cathode is considered as positive electrode, whereas electrolytic cell, it is the reverse. And in case of galvanic cell, as you see in the image, you can see the cathode and the anode are kept in two different compartments. So the anode is dipped in anodic solution, cathode is dipped in cathodic solution, and then they are connected. This is how the setup of galvanic cell is. And whenever you say the electrolytic cell, both the cathode and the anodes are fitted in the same compartment. So you see them in the same electrolyte, which are dipped in the same electrolyte. And then in the galvanic cell, since you are putting the anode and the cathode in the different compartments, you see the ions discharging at the cathode. Whereas in case of electrolytic cell, you can see the ions are getting discharged both the electrodes. This we are going to see when we do the reactions. And some of the examples for the galvanic cell are the dry cells or the lead storage batteries, which you use in the inverters at your home. And in case of electrolytic cell, it is a preparation of NaOH, which you're going to see further. So whenever you see a cell, the major thing which you have to go across, which you have to study, is the electrode potential. So potential is your capacity, right? What exactly is potential? It is nothing but the capacity. And electrode potential, the capacity of the electrode. So what it is and how is it generated? What is the origin of electrode potential? How the potential is generated? All these things we are going to see in this chapter. If you're watching, please like and subscribe the videos, and keep supporting by your comments in the comment section or the live chat section. So electrode potential, whenever you say you take a metal rod, metal electrode, and you keep it in its own salt solution. For example, before that you should remember what exactly oxidation and the reduction is. Oxidation, it's easy to remember using the mnemonic. Okay. Loss of electron is oxidation, gain of electron is reduction. That's Leo is nothing but the lion. And how does the lion make the sound? Grr, right? So loss of electron is oxidation, gain of electron is reduction. Now, so there are two ways where you can have the reactions when the metal is dipped in its own salt solution. For example, if you are placing zinc in zinc sulfate solution, or M, a metal M is kept in Mx, its salt solution. What is that you are expecting to happen? So, if the metal is very reactive, it has a tendency to donate the electron, lose electrons, it undergoes oxidation. For example, if you say zinc undergoes oxidation and it gives Zn2 plus. Zinc gives 2 electron because of its configuration, that's TDD10 4s2. It gives 2 electrons and becomes Zn2 plus. This is one of the possibilities. This is when the metal is more reactive. Instead, if you have the metal ions in the solution, so what is that you are expecting? Say you have copper sulfate, copper dipped in the copper sulfate solution. What's going to happen? The metal ions in the solution, that's Cu2 plus ions, because this exists as Cu2 plus and the SO42 minus, that gains two electrons, that gains electron and becomes copper. So here the electrons are gained, so this is a reduction. So when one metal is in its own salt solution, either the oxidation can take place or the reduction can take place. So on balancing, which is undergoing oxidation and which is undergoing reduction, all these things we are going to see now. So how the electrode potential is developed. So if you consider this, we know that copper is a less reactive element. Least reactive, you can say. When copper is kept in copper sulfate solution, what's going to happen? A very few of copper ions, say this is the copper sulfate ions, and this is a copper inside. Now, what is that you are expecting? The Cu2 plus ions, which are present, they deposit over here. And then here there is a metal, the copper, and they take electrons from this and they deposit as Cu over this. Like this. And the other case where the metal is more reactive, so metal goes to the solution, leaving behind the electrons. So this is called as anode, and it goes leaving behind the electron. So this gets a negative charge. So the metal is negative compared to the ions which are present outside. So there is a development of electrical double layer. So there's the inside the metal you can see the negative charges, and outside it is going to attract the positively charged ions, that's Zn2 plus. Because of two different layers of charges, you see the potential development. So if the metal is less reactive, that undergoes reduction, and if the metal is more reactive, that undergoes oxidation. So depending on whether it undergoes oxidation or the reduction and what charge it possesses, you can assign it as either cathode or the anode. And now, taking this into consideration, we are going to solve some problems, and also we are going to define a couple of things. The first one which we are going to see is the electrode potential. What is that? So this is going to happen until the equilibrium is reached. So here you have zinc and here you have Zn2 plus ion. When the equilibrium is reached in between those two, until the equilibrium is reached, this is going to happen. So how do you explain this electrode potential? So it's the potential development, that's a plus and the minus charge separation, when a metal is in equilibrium with its own ions in the solution. So that's called as electrode potential. Now, what exactly is single electrode? You take one electrode or one metal rod and you dip it in its own salt solution. This gives you a single electrode. You're taking only one electrode, right? That's why it's called as single electrode. And what is the difference between this electrode potential and the standard electrode potential? So if you say the electrode potential, this is the potential level of one electrode is kept in its own salt solution. And if it has to be standard, you have certain conditions. The solution or the electrolyte in which you are dipping the metal, that should have the concentration which is unity. That's 1 molar concentration. And also the temperature in which you are keeping the system, that should be 298 Kelvin. Hope you get it. In case of electrode potential, the metal is dipped in its own salt solution and there is equilibrium, and the electrode potential developed is called as, or the difference in the potential is called as electrode potential. Whereas in case of standard electrode potential, the solution or the electrolyte which you're taking, that should have 1 molar concentration and the experimental setup should be at 298 Kelvin. So on what properties does the standard electrode potential depend on? We have different things. One is what type of metal you are taking. whether it is more reactive or less reactive. What's the temperature? Since it's standard electrode potential, it's at 298 Kelvin. Otherwise, it also depends on the temperature because you don't mention the temperature and also the concentration. And now, the nature of the metal, temperature, and the concentration we are going to see one after the other. And now we are going to go for galvanic cells. The first type of cells, if you remember, I have explained it over here. The galvanic cell is the one where the chemical energy is converted to the electrical energy. So there will be spontaneous reactions out of which the electrons are generated, and these electrons carry the electricity. So the chemical energy is being converted to the electrical energy. So the example is the Daniell cell. We'll see how it is constructed. Now, in case of this, in the construction, zinc is dipped in zinc sulfate solution. This is very easy to remember. Zinc is dipped in zinc sulfate solution. This makes one compartment. And in case of galvanic cell, we know that there are two different electrodes dipped in their own salt solution, and there are two different compartments, right? And then now, zinc is dipped in zinc sulfate solution. Copper is dipped in copper sulfate solution. So you have two metal electrodes, that's zinc and copper, dipped in their own solutions, salt solution. And these two electrodes, these two metal rods, are connected through the external circuit, through the wires, and a galvanometer is kept in between. And these two solutions to maintain the charges, to maintain the neutrality, or for the movement passage of the ions, a salt bridge is kept in between. Okay, so this is the experimental setup. When the circuit is complete, like you are connecting the metal electrodes, you are connecting the electrodes and the solutions, then the electrons start moving from Zn to Cu. Why is that so? Zinc is more reactive and zinc undergoes oxidation. So what is the reaction happening at zinc? So these are called as half cell reactions. And the first half, that's zinc and zinc sulfate, this gives you half cell. The other one, the copper and copper sulfate, that gives you another half cell. So what are the cell reactions happening? Zinc, which is present in the solid state, that changes to the ionic form, that's Zn2 plus, and it gives 2 electrons. At cathode, the copper is dipped in copper sulfate solution, so that this copper gains 2 electrons, and then it becomes the copper, which is solid. And what is a net reaction? Whenever you write a net reaction, you have to cancel out the electron and include the species which are there in the cell only. So Zn, here the number of electrons are common. If they are not common, you have to make them common and multiply by a common factor, which converts this electrons into the equal number. So if you cancel it out, Zn plus Cu2 plus is going to give you Zn2 plus Cu. This is the net reaction. And this net reaction, how are you going to convert it into the cell representation? What exactly is cell representation and how do you do it? Whenever there is a cell and you have to represent it in a proper format, how do you do this? You take anode. This is how the general representation is done. Anode is generally a metal that will be in the solid form. Then there is a phase difference between the anodic solution. So whenever you say anodic solution, this will be in the liquid form or in the aqueous form. So a single line and a double line. This indicates the salt bridge. So this is half cell is over by now. And then you have cathodic solution. That's in the liquid or the aqueous form. I'm generally writing it as liquid. And then you write the cathode, which is a metal, which is a solid. So this is how the cell representation is done. You should know how to convert the cell, how to interconvert these things. Like from net reaction, how do you get the cell representation, and from cell representation, how do you convert it into the net reaction? So in this particular Daniell cell, zinc is dipped in zinc sulfate solution, separated by a salt bridge, and the copper is dipped in the copper sulfate solution. And since sulfate ions are the spectator ions and they don't participate in the cell reactions, you can eliminate them and you can write Zn bar Zn2 plus double bar Cu2 plus bar Cu. And when you write, if particular concentration is known or for these two, you can include them below the species. Okay. And now since the reactions are happening over here, the electrons start moving from this side to this side, zinc to copper electrode, and the galvanometer is going to show you the deflection in the opposite direction. The current moves in the opposite direction as those of the electrons. Now, what exactly is EMF? So the potential difference, there is a potential development in both the electrodes. So what exactly is the difference in the potential between them? That's called as EMF of the cell, electromotive force. So it is in the difference between the standard reduction potential is what you have to remember. I'm going to explain what exactly is the reduction potential of the cathode and the anode. So generally, whenever we say anode over here, in the Daniell cell I'm speaking about, or the galvanic cell, whenever you say anode, in case of anode, you see the oxidation, right? For example, Zn becomes Zn2 plus 2 electrons. So there is oxidation, and this is called as the oxidation potential of the metal or that particular electrode. It has a potential to undergo oxidation, thus to lose the electron. And at a cathode, what you see is a reduction. What exactly is a reduction? It's the ability to gain electrons. It's a potential to undergo reduction. How easily it takes up the electrons. So this is denoted as reduction potential. But according to the rules, we don't use the oxidation potential. Instead, we change it to the reduction potential. So we don't mention anything in terms of oxidation potential. Instead, we use it as a reduction potential. Okay, so if it has some value, say plus x, the oxidation potential is plus x, is its ability to undergo oxidation. Whenever you write the reduction potential, this becomes minus x. So this has a less interest. This is not more interested in undergoing reduction. So its sign becomes negative. Now, how do you represent E cell? So you have the half cell, that's anode, the other half cell, which is cathode, and they are clubbed together and they are connected and the circuit is complete. Now the electrons move and the electricity is generated, and you write E cell, which is equal to the cathode, the reduction potential of cathode minus that of anode. That's how you write. And how do you identify? So you don't understand all this stuff and everything gets confused in the exam. It's easy to remember. We mention everything in terms of reduction potential, isn't it? So what is reduction potential? It's the potential to undergo, ability to undergo reduction. So higher is the E value, they'll give you the E value, this value, reduction potential value. Higher is the E value, more ability or more interest or more potential to undergo reduction. Higher or positive. And lower value, lower E value, that undergoes oxidation, and you can directly take it as anode and you can take it as cathode. So whenever two electrode potential values are given, the one which is with the higher value, that's considered as cathode, and that's where the reduction happens. The other thing is the one will be the anode, where the oxidation is going to happen. And you write EMF of the cell, which is equal to E cathode minus E anode. And at the end, always you should get EMF as positive. Then only it's right. Okay, let's take some of the reactions happening, or some of the examples by which you are going to calculate the cell potential. How are you going to calculate the cell potential? That's what you are going to see now. Yeah, we'll move ahead with this one. What is the potential of the following cell? So you are given with the cell, and you should remember how it is represented. If you know the cell representation, it's very easy. If you don't know the cell representation, it's okay. You can follow the values which are given over here. How do you calculate this? What is the potential of the following cell? How do you calculate? If you are watching this, you can help me out. How do you do? Ag to Ag plus. The first one, what is the cell representation of this? We do the cell representation as anode, anodic solution, double bar, cathodic solution, bar cathode. So, what is the potential of the following cell? How do you calculate it? You give me the ideas how to calculate this, and if you're watching this, and we can proceed with the further examples. How are you going to calculate this? Generally, it has to be this way always. Anode is the one which are the anode is the one where the oxidation happens. So what's oxidation? Loss of electron. So I can also represent this as this in the form lithium. What its ability to undergo? It loses the electron to give Li plus, double bar, Ag plus, bar Ag, because if you see the conversion of Li plus to Li, that's Li plus undergoes, this is a reduction reaction, right? So that's negative. That means it has the capacity to undergo oxidation, right? So Li plus to Li, that's E naught is equal to minus 0.34, minus 3.045, and Ag bar Ag plus is forget about the concentration because we don't need that. They have just asked the potential. Ag undergoes reduction, sorry, here Ag to Ag plus, it undergoes oxidation, and the oxidation potential is mentioned like this. So generally, whenever I say E and E naught values, this should be expressed in terms of reduction potentials. So by taking these values now, you can calculate the potential using E cell is equal to E naught cathode minus E naught anode, where E naught is the standard potential, a standard electrode potential, and E is called as just the reduction potential. So you're given with the cell representation, you can write the cell reaction as well. We'll consider everything put together. So we'll start with this one. How do you write the cell representation? You identify the species first. You make it into two parts. Zn undergoes oxidation to give Zn2 plus. How do you get Zn2 Zn2 plus charge? When a substance gains positive charge, when it is a cation, it loses the electron. So electrons are lost. We are writing the electrons on the product side. This is called as oxidation. And the other one, that's a cadmium that takes up 2 electrons. Since Cd2 plus to Cd, you are going to get Cd. This is called as reduction. Now, how do you write the cell representation? It's anode, bar anodic solution, double bar, cathodic solution, bar cathode. This is how you write. Okay. What is the anode over here? That's Zn. What's the anodic solution? Zn2 plus. That's, you can write it as aqueous, salt bridge, and then cathodic solution is cadmium 2 plus. That's the aqueous. And then you have cathode, that's Cd. This is how you write the cell representation. Isn't it easy? We'll go for the next one now. The EMF of the cell, they have given you the EMF of this whole cell, and then write the half cell reaction and calculate the pH of the solution at the hydrogen electrode. We can calculate the pH later because I'm going to take it at the end. Just give me how to calculate the EMF is given. So how do you write the cell reactions of this one? How are you going to write it? What are the steps you're going to follow to write them? So how do you write the cell reactions? Zn becomes Zn2 plus and it gains 2 electrons, and then the next one is 2H plus becomes H2 by taking 2 electrons. And how do you write the half cell reactions? These are the half cell reactions. And now how do you give the cell representation? Zn bar Zn2 plus bar H plus bar H2. You need not include the overall that's 2H plus in the equation, and if you are a representation, if you write it also, it's not wrong. Okay, and now we'll go to the pH calculation part later. So in case, I'm just erasing all these things. In case there is a cell constructed using the aluminum and the so how do you write the cell reactions? Al and say this is a reaction they have given you. You are supposed to write the cell reaction as well as the half cell equations. How are you going to write them? First, since the representation involves anodic solution, we'll write the anode reactions first. That's Al is going to give you Al3 plus, and it gives you 3 electrons because Al changes to Al3 plus by giving the 3 electrons, and then you have Cu plus that takes up an electron and becomes Cu. So the reduction is happening here. Now, if you have to write the overall reaction, you have to cancel out the electrons, and when you cancel out the electrons, the number of electrons in both the cases should be equal. So what you do, there are 3 electrons here, so there is only 1 electron here. How do you make it 3? By multiplying this whole equation by 3. So you have Al, which gives you Al3 plus 3 electrons, and the second equation, that's 3Cu plus gives you 3Cu plus 3 electrons is going to give you 3Cu. Now you cancel out the electrons and you write the cell overall net equation as Al, and 3Cu plus is going to give you Al3 plus 3Cu. This is the overall. You can write aqueous wherever it is needed, and the solid state. So you have to make the number of electrons equal. Then we come across the next topic that's very important. What exactly is SHE? That's a standard hydrogen electrode, and how is it constructed, and what is the use of it? Why do you need that? So in all these calculations, whatever we see, if you have seen, you get the E naught values, right? What exactly is E naught value? That's called a standard electrode potential or standard reduction potential. Standard reduction potential value. How do you get the standard reduction potential values? You can get E cell. Just you connect 2 different electrodes and you see how the galvanometer is fluctuating, and from that you can calculate E cell. But if you want the individual reduction potential value of these 2 electrodes, how are you going to achieve them? That is where the SHE comes into picture. It's like, say you have connected electrode A with electrode B, and you get some deflection in the galvanometer that reads as say 1.5. Now, how do you achieve for better calculations? I'll keep it as 2.0. Okay, let me erase everything and rewrite again. So you have connected an electrode, one electrode, that's an anode and anodic solution, cathode and the cathodic solution. You connect it using the galvanometer, and then you have the salt bridge which is connecting 2 solutions. Now, say you get the deflection as 2.0 volt. So how do you get that? E cathode, E naught cathode minus E naught anode, which is going to give you 2 volt. That's nothing but the EMF of the cell. How can you achieve that? It can be 1 and minus 1. You get 2, or 1.5 and minus of minus 0.5, and you can even take 2.5 minus 0.5. So all these are going to give you 2 volt. That means if both the electrode potentials are unknown, you will get just the EMF but not the individual electrode potential values. It's like x plus x is equal to 10. Both x can be anything, or x plus y is equal to 10. You can give numerous values for x plus x and y, but if you know what exactly is x, you can easily find out y. So if it is x minus y is equal to 2, and if they give you the value of x, you can easily find out y. Now, to find out individual electrode potential, what exactly is x, what exactly is y, you have to go for standard hydrogen electrode. Why is it constructed? To know the individual electrode potential values. So what are you doing over here? What is the construction type? You take a platinum foil, coat it with the platinum black. So platinum powder, can you see this one, the lower portion here? Yes, here. This is a platinum foil. It's coated with platinum powder because that gives you the large surface area and more adsorption of hydrogen will be observed. Now, this is connected to the external circuit using a copper wire, and this has a thin jacket so that the copper doesn't react with anything. It will not react. And outside you have an outer jacket which has an inlet at the top. You can see this is the outer jacket with the inlet at the top where hydrogen gas is passed at 1 bar pressure. And the entire setup is dipped in 1 molar HCl solution. So this is the experimental setup. And inside you have the hydrogen gas at 1 bar pressure, that's inside the tube, and outside here there is a HCl, 1 molar HCl. So over the surface of this platinum foil, this is in touch with both the gas and also the liquid, that's a HCl. When there is equilibrium established between H plus in the aqueous solution and also the H2 on the surface, what's going to happen? There is an equilibrium. So H plus, you can write the reaction the other way too. H plus gains an electron and becomes half H2. This is a cell reaction which happens at the SHE, that's a standard hydrogen electrode. Now, its electrode potential value is taken as 0, the voltage produced. And then, how do you represent this? There is only one electrode over here. So, the H plus, since this reaction is a cathode, because gain of electron is called as happens in case of cathode. So, how do you represent the cathode? Cathodic solution bar cathode, right? So H plus bar H2, and this is over the surface of platinum. We add something more. We don't use the salt bridge, so there is no double bar. So H plus is at 1 molar and H2 is at 1 bar and platinum is a solid. This is how we give the cell representation. Okay, now let's move on to the next topic. Why and where do you use it? Now you know the value of potential of standard hydrogen electrode, that's taken as 0. Using this, you are going to find out the hydrogen electrode. You are taking hydrogen electrode and finding out the electrode potential of various other electrodes. So now take Zn and connect it with hydrogen and see the deflection values. Did you understand what I mean? Now you have to construct. If you just construct a zinc and copper, say this is zinc and copper, you are going to connect them like this. This is zinc, this is copper. You see the galvanometer deflection, it gives some value, say 1.1 volt. You don't know what is the electrode potential of zinc and what is the electrode potential of copper. Now what you do, once you get the standard hydrogen electrode, you take the standard hydrogen electrode over here like this. I'm representing this way. So these are connected and say the galvanometer deflection is going to give you 0.76 volt. Do you understand? Now, how do you calculate E cell? E cell is equal to E cathode minus E anode. Now, what is cathode? The standard hydrogen electrode, 0 minus 0.76, which is equal to minus 0.76 volt. This is the electrode potential of anode, that's a zinc. This is how you get the electrode potential of individual electrodes. And how are you going to represent the cell? How are you going to represent the cell here? Zinc Zn bar Zn2 plus double bar H plus bar H2 over the surface of platinum. For hydrogen electrode, wherever you connect, you have to give H plus bar H2 bar platinum. Okay, so by this way, if you want the electrode potential, individual electrode potential or the standard reduction potential of copper, then what you are going to do, you're going to connect it with the hydrogen electrode, standard electrode, hydrogen electrode. You see the deflection of that particular galvanometer. Using that, you apply the formula E cell is equal to E cathode minus E anode, and you get the value of the copper electrode. So anything can be coupled with the standard hydrogen electrode, and its individual electrode potential value can be found out taking the electrode potential of hydrogen, standard hydrogen electrode as 0. Okay, yeah. So you can find out any value. So the positive value of standard electrode, if the standard electrode potential is positive, what does that mean? That means they get reduced easily compared to H+. H+ has 0 value. The reduction potential of hydrogen is 0. So, and the reduction potential of zinc is negative. That means zinc doesn't undergo reduction easily. Instead, it undergoes oxidation. That's why you get a negative value. If you get a positive value, that means that particular metal undergoes reduction. Since it's a reduction potential, the capacity to undergo reduction is more. So the reduction potential is high. You get a positive value. Okay, so in case if you keep copper in HCl solution, what do you mean by that? Copper won't react with HCl solution, because in this reaction, if it has to react, it should get converted to Cu2 plus or Cu1 plus, whatever. And this is called as oxidation. The copper doesn't oxidize in the presence of any acid. Okay, and then there are some electrodes which participate in the cell reaction. They are the active electrodes like zinc and copper and all. There are some metals like which are very inert. They are inactive and found in the native state in the earth crust, like platinum and the gold. They are used as inert electrode because they do not participate in a reaction. They are highly stable and they do not get oxidized during the reaction. Okay. Okay, this is all about the half reaction and the standard potential values. We will see what is the use of it. If you see this, the highly reactive metals have this is the reduction happening. Can you see that? In every place, the electrons are being added. So this is called, you can consider all these reactions as reduction. Fluorine, we know that fluorine gains the electron. There are some species which gain the electrons. So when they gain the electron, they undergo reduction. Fluorine has highest electronegativity, so it can accept the electron quicker. So it undergoes reduction. If it undergoes reduction, its reduction potential value must be higher. So the one which undergoes reduction fast is considered as the strongest oxidizing agent, because oxidizing agent is the one which helps for oxidation, but it gets reduced. If you take the metals like lithium, sodium and all, that's a group 1 elements. What is that you are expecting? So say lithium, these are highly electropositive, so they have the tendency to undergo oxidation. They undergo oxidation very easily. So they act as strongest reducing agents. And since they undergo oxidation easily, their reduction potential values will be negative. These are very less. This is what you can conclude from the electrochemical series. This is called as electrochemical series. It is the arrangement of different elements in the order of their ability to undergo reduction. So what is the significance of this electrochemical series? So if you see the standard electrode potential of lithium, that's some group 1 or group 2 elements at the bottom, it's very high, indicating these undergo oxidation very quick. The one which undergoes oxidation can act as a powerful reducing agent. And on the other hand, after it becomes Li plus. What it is? Li plus gains an electron and becomes Li. So this is the weakest oxidizing agent. Then the standard electrode potential, if you see the fluorine ozone on top, it gains the electron very quick. So it undergoes reduction. That means it is a powerful oxidizing agent. And if you see anything which is hydrogen is there over here. This is taken as 0. Anything which is above hydrogen that will not react with acid faster and that doesn't liberate hydrogen gas, and anything which is below hydrogen that will react with any acids and produces hydrogen gas. That means standard reduction potential of any electrode, if it is above zero, that's if it is positive, then its reduced form is more stable. So Cu2 compared to Cu2 plus and Cu is more stable. Its reduced form is more stable. And if the reduction potential is lesser than zero, they are below hydrogen, their oxidized form or hydrogen is more stable than them. So they liberate hydrogen gas. Okay. We'll quickly go to some of the questions over here. And yeah, there is one more thing, Nernst equation. Why do you need this? So if you see the standard reduction potential, these are under standard condition where you dip an electrode in its own salt solution having 1 molar concentration and also the temperature is 298 Kelvin. Now, if you have any values other than this, so the concentration is not 1 molar and the temperature is not over 298 Kelvin, then what you get is just a reduction potential, not the standard reduction potential. How are you going to calculate these values? That's what you have to see. So for that, if a metal undergoes reduction, the general equation which is given over here is the reduction equation, where the metal with charge N plus gains n electrons and becomes M. This is a reduction reaction. And using this, because since we express everything in terms of reduction potential, we explain the reduction reactions only. Okay, don't consider any oxidation reactions over here. Now, a scientist called as Nernst, he gives an equation from which the electrode potential values can be determined, which are not in the standard conditions. So this is a reduction, and E, that's a reduction potential. The reduction potential of Mn plus to get converted to M, which is equal to this E naught, naught stands for standard conditions, minus RT. R is gas constant, T is the temperature, N is the number of electrons transferred, that's N electrons, F is the farad, which is 96,500. That's a constant value which you are going to take, which is called as Faraday's constant, and Lan, concentration of the metal, the concentration of this one over the concentration of the corresponding ion. Since this is present in the solid form, we consider its concentration as unity. So the equation changes to E, which is equal to E naught minus RT divided by NF Lan. The concentration of this is unity since it's a solid, and you get this type of equation. Now, if you apply, this is for single electrode, right? You have only one reaction happening. If you have two reactions happening, that's if you have a cell where the oxidation and the reductions are happening simultaneously, and you have the oxidation half cell, you have the reduction half cell, and what you do, that's Zn gets converted to Zn2 plus, that's Zn undergoes oxidation, copper undergoes reduction. Then Zn, we'll consider half reactions only. Zn plus 2 plus bar Zn is equal to E naught minus RT divided by NF. N is 2 electrons are transferred over here by 2F Lan of the concentration of solid, that's Zn, that's directly taken as 1, over the concentration of Zn2 plus. For cathode, the same way, ECU2 plus bar Cu, which is equal to E naught minus RT, here also 2 electrons are being transferred to F Lan of the concentration. Now the cell potential, what do you write the cell potential? E cell is equal to E cathode minus E anode. So E cathode is nothing but this one minus this one is going to give you this values. Since the E cell is equal to E naught minus E naught, this is E naught cell under standard condition, cell potential under standard condition, which is equal to RT by N. N is 2 common log of, this is log A 1 by A divided by log of 1 by B, that becomes log this one. When you minus it, it becomes plus log of Zn2 plus bar Cu. Or if you put the constants over here, R, T, F values, if you put, you are just left with, and the Lan, your Lan you convert it to log by multiplying by 2.303. At the end, you will be having the final equation. E cell is equal to E naught cell 0.0591 divided by N. N, it should be N, but in this particular reaction, the number of electrons transferred is 2 log of Zn2 plus by Cu2 plus. That means if you have an equation of the form AA plus BB gives rise to CC plus DD, where A, B, C, D are the stoichiometric coefficients which you use for balancing. Then E cell is equal to E naught cell minus RT divided by NF, or you can directly take 0.0591 divided by N only, log of concentration of the product divided by concentration of the reactant, which you have to take only in the aqueous form. Whenever you say product and reactant, you have to take them in the aqueous form, and whatever the numbers are there for balancing, they become the powers. So if you have an equation like this, here the number of electrons transferred are 2. So when you balance the whole equation, here also you're going to make the number of electrons 2. So E cell is equal to E naught cell minus 0.0591. The number of electrons transferred is 2. Log of concentration of the product. The product is nothing but, which is the product over here? How do you write this equation? You write the equation as Ni plus Ag plus gives, you should know how to write this equation, that gives Ni2 plus 2Ag. You balance this reaction. Now, which is the product? These two. This is a solid. Ignore it. You just put Ni2 plus concentration. And this one, Ag plus, and this number becomes the power. This is again a solid. You ignore it. So this is how you write the equation, and if the concentrations are given, you just apply and get the final value. This is what you are going to do. Do you understand that? So I want you to mug up this equation, the final equation, where you get E cell and what's the relationship with E naught cell, and how do you get the cell reaction, cell representation, cell equations, everything, which should sit in your mind in the next class, and so that we can go faster and very quick, and we can solve together so many problems. Okay. So this is a MCQ corner where you have a couple of questions which you can answer. If you're watching this video, you can type down your answers. I'm waiting for it. Yeah, can you be please quicker? Waiting for your answers. Saturated solution of KNO3 is used as a salt bridge. You know what exactly is salt bridge, which connects two solutions, right? Because what is the reason? This is pretty easy. How do you get that? What you can do over here? Yeah, here velocity of K plus is greater than NO3 minus, velocity of NO3 minus is greater, KNO3 is highly soluble. If it is highly soluble, you can even use some other salts as well, right, which are highly soluble. It is because the velocities of both the ions which the salt bridge is going to produce, the salt is going to produce in the salt bridge should be similar. It need not be exactly the same, but they should be similar. They should have the same order. That's why. Which is the correct equation of standard Nernst equation? If you forget this, just take the equation of the Daniell cell. Zn plus Cu2 plus is going to give you Cu plus Zn2 plus. How do you write the final expression? Zinc is undergoing oxidation. So this is a reducing agent, and this is an oxidizing agent. Now, how do you write the equation? And E cell, which is equal to E naught cell minus 0.0591 divided by N log of concentration of the product, that's Zn2 plus divided by Cu2 plus. What is Cu2 plus? This is oxidant. Okay. What is Cu2 plus? The one Cu2 plus undergoes reduction, so this should be oxidizing agent. Just check. The first one, E reduction potential is equal to E naught reduction potential. Oxidant comes on the top. So this is right because Cu2 plus is on the top, then you get a plus sign. So this is right. E oxidation potential, they have given in terms of oxidation potential. You reverse this equation, then also it is right. E oxidation potential is equal to, you have interchanged these two, so this is also right. You can say all of this are right. Okay. So whenever you interchange in the log term, if you interchange the numerator and the denominator, the before sign that changes. When a copper wire is immersed in a solution of AgNO3, the color of the solution becomes blue because copper. So it's like copper is dipped in AgNO3 solution, and what you expect, copper is going to react with Ag plus, and you change it as Cu2 plus or Cu1 plus plus Ag. This is what you expect. And if you see this copper, what is happening? Cu changes to Cu2 plus, thus increasing the oxidation number from 0 to 1. So copper is oxidized to Cu2 plus. That's the right answer. Option 2. E0 for Fe2 plus and 2 E electrons is given, and E0 for Zn is given. Thus, which is more electropositive? So whenever you say the E0 values, that stands for reduction potential, standard reduction potential. So if it is higher, then the one that undergoes reduction. If it's lower, that undergoes oxidation. The one which undergoes oxidation is the loss of electron. Oxidation is nothing but the loss of electron. The one loses electron should be the most electropositive. So if you see the values, this is minus 0.44 and this is minus 0.76. Among these two values, this value is lesser. So the one which is lower value will be more electropositive. So zinc is more electropositive than iron. That would be the right answer. If an iron rod is dipped in the copper sulfate solution, so what do you see? Iron rod. Iron rod is Fe, is dipped in the copper sulfate solution. This is a blue solution. What you get? You change it to FeSO4 plus Co. So the color of the blue solution fades, and this copper gets deposited over the iron which is present. So the color of the copper is nothing but the brown. So the copper gets deposited on the surface of iron rod. Whereas if you take the reverse reaction, that's ferrous sulfate plus copper, then you can see option 3, because the iron can displace copper, but copper can't displace iron. The standard reduction potentials are given, which is the strongest reducing agent. Again, you have to apply the same theory. Strongest reducing agent is the one which undergoes fast oxidation. What is oxidation? Loss of electron. Which loses the electrons faster, that will be the best reducing agent. And the one strongest reducing agent which undergoes fast oxidation, that means it will have the lowest E0 value. If you see the values, lowest E0 value will be for zinc. So which is the strongest reducing agent? This one, zinc. Each of 3 metals X, Y, Z were put into aqueous solution of the other 2. Which observation is probably incorrect? This is the question. So if you see, this is from the electrochemical series. Most reactive, in terms of simplest form, most reactive element displaces less reactive element from solution. Now, X displaces Y or Z from the solution, so X is more reactive. So Y plus salt X. Now Y is less reactive, so Y can't displace X, so no reaction observed. This is right. The question is which is probably incorrect. Whenever you see the question, you have to see whether it is incorrect or correct. Y plus salt of Z. This we don't know, because they have told X is more reactive than Y and Z, but they have not given anything in terms of Y or Z, like which is more reactive. So we don't know this option. We'll explore the other options. Third one, Z plus salt of X. Z is less reactive, you can see, plus salt of X. This can't happen because X is more reactive. Z cannot displace. This we don't know. Z plus salt of Y. So option 2 and 4 we don't know because there's no enough information, but the 3 can never happen. The less reactive Z cannot displace the more reactive X. That's all, people, for today. I hope you enjoyed today's session, and if you like our classes, please click a like button and subscribe, and keep supporting us, keep supporting the SPSVERSITY.